For the first time in over 50 years, humans are heading back toward the moon. Not as a one-off achievement, not as a race against another nation, but as the beginning of something much bigger. Artemis 2 is the mission that changes everything, and if you've ever looked up at the night sky and wondered what comes next for human space exploration, this is your answer. To understand why Artemis 2 is such a monumental moment, we need to go back to December 1972. That was the last time any human being traveled beyond low Earth orbit, the region of space where the International Space Station orbits today, just a few hundred miles above our heads. The crew of Apollo 17 were the last people to make that journey, and when they came home, that chapter of human exploration quietly closed. For over 5 decades, we have been confined to that narrow band of space just above our planet. Artemis 2 is the mission that finally breaks that boundary again. But this isn't just about nostalgia or about recreating what Apollo did half a century ago. Artemis 2 is the first crewed flight of the entire Artemis program, meaning it is the first time NASA has put astronauts aboard the Orion spacecraft and sent them on a real mission beyond Earth's orbit. And the weight of that fact is hard to overstate. Every system, every piece of hardware, every safety procedure that will one day carry human beings to the surface of the moon, it all has to be proven here first. Artemis 2 is where we find out whether all of it actually works with people on board. That's what makes this mission the critical link in the chain. Because beyond Artemis 2 lies Artemis 3, the mission currently planned to return humans to the lunar surface for the first time since Apollo. But NASA cannot go there, cannot take that next enormous step until Artemis 2 has done its job. The moon landing doesn't happen without this mission succeeding first. So when you hear Artemis 2 described as a test flight, don't let that word undersell what's happening. Yes, it's gathering data. Yes, it's verifying systems. But it is doing all of that with a real crew, on a real trajectory, pushing further into deep space than any human has gone in living memory. This is the moment the road to the moon gets real. Over the course of this video, we're going to break down everything you need to know about Artemis 2, the crew, the spacecraft, the mission profile, and what it all means for the future of human spaceflight. So, let's get into it. Every great mission has a crew behind it, and the 4 astronauts chosen for Artemis 2 are not just highly qualified, they are historic. When this spacecraft leaves Earth, it will be carrying people who will make history in ways that extend far beyond the mission itself. So let's meet them. Commanding the mission is Reed Wiseman, a NASA astronaut and former Navy test pilot who previously served as chief of the astronaut office. Wiseman is a seasoned spacefarer who has spent time aboard the International Space Station, and he brings exactly the kind of calm, experienced leadership you want at the helm of a mission this significant. Joining him as pilot is Victor Glover, and his place on this crew carries a meaning that goes well beyond his impressive credentials. When Artemis 2 swings around the moon, Victor Glover will become the first person of color ever to travel beyond low Earth orbit. Let that sink in for a moment. Human beings have been launching into space since 1961, and in all that time, in all of the Apollo missions, in every crewed flight that has ventured beyond our planet's immediate neighborhood, no person of color had ever made that journey. Artemis 2 changes that. Glover is a former Navy fighter pilot, a NASA astronaut who has already lived and worked aboard the International Space Station, and he brings an extraordinary depth of experience to this crew. Then there is Christina Koch, and her place in this story is equally landmark. Koch will be the first woman ever to travel beyond low Earth orbit. In the entire history of human spaceflight, in every mission that has pushed past the boundary of Earth's neighborhood and out into deep space, no woman had made that crossing. Until now. Koch is no stranger to making history. She previously set the record for the longest single spaceflight by a woman, spending 328 days aboard the International Space Station. She is one of the most experienced astronauts on this crew, and her presence on Artemis 2 is a moment that generations of women in science and exploration have been working toward for decades. Rounding out the crew is Jeremy Hansen, a Canadian Space Agency astronaut and former Royal Canadian Air Force fighter pilot. Hansen's selection makes him the first non-American astronaut ever assigned to a lunar mission, a first not just for Canada, but for any nation outside the United States in the history of crewed deep space exploration. His inclusion is a reflection of the international partnerships that define the modern era of spaceflight, and it sends a clear message that humanity's return to the moon is not just an American endeavor. For astronauts, for remarkable individuals, and between them, milestones that span race, gender, and nationality. When Artemis 2 makes its journey around the moon, it will do so carrying a crew that looks like the world it represents, and that matters just as much as the destination. To send 4 astronauts beyond low Earth orbit for the first time in over 50 years, you need a rocket and spacecraft capable of doing something that hasn't been done in a very long time. But this isn't Apollo. This is a new generation of spacecraft, built with decades of additional knowledge, technology, and hard-learned lessons behind it. Let's talk about the machines making Artemis 2 possible. The rocket carrying the crew off the launch pad is the Space Launch System, known as the SLS. This is NASA's most powerful rocket since the Saturn V, the legendary vehicle that carried the Apollo astronauts to the moon. The SLS has been in development for years, and it finally had its uncrewed debut during Artemis 1 in late 2022, where it performed beautifully. But Artemis 2 will be its first crewed flight, and that distinction changes everything. Flying without a crew is one thing. Every system has to work, but there is no human cost if something goes wrong. Flying with 4 astronauts on board is an entirely different proposition, and the pressure on this vehicle to perform is immense. The SLS is a behemoth, a rocket of genuinely staggering scale, producing millions of pounds of thrust at launch, and it is the only vehicle currently capable of sending the Orion spacecraft on a direct trajectory beyond Earth's orbit. Sitting on top of that rocket is the Orion spacecraft, and like the SLS, Artemis 2 marks its first crewed mission. Orion flew without a crew during Artemis 1, completing a journey around the moon and returning safely to Earth, a crucial proving exercise. But once again, flying with people on board is the real test. Orion is purpose-built for deep space travel in a way that vehicles like the SpaceX Crew Dragon simply are not. It has a larger heat shield than any crewed spacecraft ever built, designed to handle the extreme temperatures of re-entry at the speeds you reach coming back from deep space, significantly faster and therefore significantly hotter than returning from the International Space Station. Inside, it is designed to sustain a crew of 4 across missions that venture far beyond the safety net of low Earth orbit, where a quick emergency return to Earth is not an option. But Orion doesn't operate alone. Attached to the spacecraft is the European Service Module, contributed by the European Space Agency, and it is absolutely fundamental to the mission. The Service Module is essentially the engine room of the Orion spacecraft. It provides the propulsion needed to maneuver in deep space. It generates the electrical power that keeps the spacecraft running, and it supplies the oxygen and water the crew depends on to survive. Without the European Service Module, Orion cannot function. Its inclusion is also a powerful symbol of what modern spaceflight looks like: an American crew in an American spacecraft kept alive and moving through deep space by hardware built in Europe. This is a genuinely international endeavor at a hardware level, not just in name. Together, the SLS, Orion, and the European Service Module form a system that represents the most capable crewed deep space architecture humanity has ever built. Apollo was extraordinary for its time, but Artemis 2 carries the knowledge of everything that came after, and the ambition of everything still to come. So we have an extraordinary crew, a powerful rocket, and a next-generation spacecraft. But what is Artemis 2 actually trying to do? What is the point of the mission beyond the milestone of simply getting there? The answer to that question is what separates Artemis 2 from a publicity stunt and makes it one of the most important flights in the history of human spaceflight. This mission is about proof. It is about standing at the edge of deep space with 4 human beings on board and asking the hardest possible question: can we actually do this safely? Artemis 2 is officially classified as a full flight test. That classification is important because it shapes everything about how the mission is structured and what success looks like. Unlike a standard operational mission where the goal is a specific destination or objective, a flight test is about the journey itself. Every system, every procedure, Every piece of hardware gets scrutinized. Every reading gets logged. Every anomaly gets noted. The mission is, in its entirety, an exercise in verification, and the stakes of that verification could not be higher because what comes next depends entirely on what this mission proves. At the top of the list is life support. When you are in low Earth orbit aboard the International Space Station, you are never more than a few hours from Earth in an emergency. The infrastructure of rescue, resupply, and return is never far away. In deep space, that safety net disappears entirely. The systems keeping the Artemis 2 crew alive, the air they breathe, the water they drink, the temperature of the cabin, the removal of carbon dioxide, all of it has to work reliably and autonomously, far from any possibility of outside intervention. Artemis 2 will push those life support systems into the deep space environment for the first time with human lives depending on them, and the data gathered will be critical to understanding how they perform under real conditions. Navigation and communications face an equally demanding test. Operating in deep space introduces challenges that simply don't exist closer to home. Signals take longer to travel. The spacecraft's position relative to Earth changes constantly and dramatically. The precision required to navigate accurately, to maintain contact with mission control, and to execute maneuvers correctly in that environment has to be proven before anyone can responsibly commit to sending a crew all the way to the moon. Artemis 2 provides the opportunity to validate all of those systems under genuine deep space conditions, with real consequences if something doesn't perform as expected. And then there is the environment itself. Deep space is a fundamentally different place to the relatively sheltered region of low Earth orbit. Beyond Earth's protective magnetic field, the crew and spacecraft are exposed to higher levels of radiation, to temperature extremes, and to a range of environmental conditions that are difficult to fully replicate in any ground-based simulation. Collecting real data from inside that environment, how the spacecraft responds, how the hardware holds up, what the crew actually experiences, is invaluable in a way that no amount of modeling or testing on the ground can fully substitute for. This is why Artemis 2 matters so profoundly. Not because it lands on the moon, it doesn't. Not because it breaks records for distance, it won't travel as far as the Apollo missions did. It matters because it is the rigorous, methodical, human-carrying proof of concept that every mission beyond it depends upon. You cannot responsibly land people on the moon without first proving that the systems designed to keep them alive and in control actually work in deep space. Artemis 2 is how we earn the right to take the next step. Everything we have talked about so far, the crew, the spacecraft, the purpose of the mission, all of it leads to a single moment. The moment the engines ignite, the ground shakes, and Artemis 2 leaves the Earth behind. Let's walk through what that actually looks like, from the launch pad to the point where the crew turns their backs on our planet and heads toward the moon. Launch takes place from Kennedy Space Center in Florida, from the same historic launch Complex 39B that supported the Artemis 1 mission. When the Space Launch System ignites, the scale of what's happening is almost difficult to comprehend from the outside. Millions of pounds of thrust firing simultaneously, the sound alone capable of being felt miles away, and 4 human beings sitting at the top of it all, trusting in thousands of engineers and decades of accumulated knowledge to carry them safely off the surface of the Earth. It is one of the most dramatic and technically demanding moments in all of spaceflight, and for Artemis 2, it carries the additional weight of being the first time the SLS has ever done this with a crew on board. But the mission doesn't immediately set off for the moon the moment it clears the launch tower. What happens in the period immediately following launch is just as important as the launch itself, and it is a phase of the mission that doesn't always get the attention it deserves. After reaching space, Artemis 2 enters what is known as a high Earth orbit phase, a period where the spacecraft remains in the vicinity of Earth while the crew and mission controllers on the ground run through a comprehensive series of systems checks. Think of it as the last opportunity to look everything over before committing to deep space. Once Orion leaves the gravitational embrace of Earth and heads out toward the moon, the options available in an emergency narrow significantly and very quickly. The high Earth orbit phase is therefore a critical window, A chance to verify that the spacecraft systems are all functioning correctly, that life support is performing as expected, that communications are solid, and that the crew are in good condition before the point of no return is crossed. If something isn't right, this is the phase where there is still a realistic option to bring the crew home relatively quickly. It is caution built into the mission architecture by design, and it reflects the hard-learned wisdom of human spaceflight programs across the decades. What makes Artemis 2 particularly interesting is that it follows a unique orbital profile on its way out from Earth. Rather than a straightforward trajectory directly toward the Moon, the mission is designed around a carefully calculated path that serves the testing objectives of the flight. The orbital mechanics involved are complex, but the underlying principle is straightforward. Every phase of the outbound journey is an opportunity to gather data, stress test systems, and verify performance in conditions of increasing distance from Earth. The trajectory isn't just a route from A to B. It is itself part of the experiment. There is something deeply human about this phase of the mission when you sit with it for a moment. The crew will be orbiting Earth, looking down at the planet they have just left, running through checklists and confirming readings, knowing that very shortly they are going to cross a boundary that no human being has crossed in over 50 years. The high Earth orbit phase is where the reality of what is about to happen must settle in fully for the crew, for mission control, and for everyone watching from the ground. The checks come back clean. The systems are go. And then Artemis 2 points itself toward the Moon, and the next chapter begins. The systems checks are complete. The crew are healthy. The spacecraft is performing. And now comes the moment that separates Artemis 2 from every crewed mission in the past half-century. The engine burn that sends 4 human beings toward the Moon. In the language of spaceflight, this maneuver has a name: translunar injection. It sounds technical, and the physics behind it certainly are, but the concept is elegant in its simplicity. The European Service Module's engine fires for a calculated period of time, accelerating Orion beyond the velocity needed to stay in Earth's orbit, and from that point forward, the spacecraft is no longer circling our planet. It is falling toward the Moon. Gravity, trajectory, and timing all working together to carry the crew across roughly 250,000 miles of deep space. Translunar injection is the point of commitment. It is the burn that makes Artemis 2 a lunar mission in every meaningful sense of the word, and when it completes, the crew of 4 will have already traveled further from Earth than any human being has since the final Apollo mission over 50 years ago. But perhaps the most important thing to understand about the journey to the Moon on Artemis 2 is not just where the spacecraft is going, it is how it is going there. The mission is designed around what is called a free return trajectory, and this is one of the most significant and carefully considered decisions in the entire mission architecture. A free return trajectory is, at its core, a built-in rescue plan. It means that the path Orion travels on its way to the Moon is calculated, so that if the propulsion system fails completely, if the engine cannot fire, if something goes critically wrong, and the crew loses the ability to make any further maneuvers, the spacecraft will still come home. The physics of the trajectory itself, the gravitational influence of the Moon curving the spacecraft's path, will naturally carry Orion back toward Earth without a single additional engine burn required. That is an extraordinary piece of engineering philosophy. It means that at almost no point during the outbound journey is the crew ever truly stranded. The mission is designed so that the universe's own physics serve as a backup safety system. For a flight test of this magnitude, operating in deep space with 4 human lives on board, that margin of safety is not just reassuring, it is essential. It reflects the same conservative, methodical thinking that runs through every aspect of how Artemis 2 has been designed, where the question is never just how do we get there, but what happens if something goes wrong, and how do we ensure the crew survives it. What makes this particularly notable is that Artemis 2 will be the first crewed mission to fly this modern incarnation of the free return trajectory. While the concept itself draws on principles that were understood during the Apollo era, the specific trajectory profile being used for Artemis 2 represents a contemporary approach, refined with decades of additional computational power, orbital mechanics research, and mission planning expertise. The Apollo missions used free return trajectories in their early flights, before later missions modified their paths to allow for more complex lunar operations. Artemis 2 brings that safety-first philosophy back to the forefront, appropriate for a mission whose entire purpose is to prove that the system works before the stakes are raised any further. So picture it from the crew's perspective. The engine burn completes. The spacecraft is quiet again. And outside the windows, the Earth is already beginning to shrink, slowly at first, and then with an increasing sense of scale that no photograph or simulation can truly prepare you for. Ahead of them, the moon is growing. And beneath their trajectory, carved invisibly into the mathematics of space and time, is a path that will bring them home no matter what. Artemis 2 is on its way. There is a moment that every astronaut who has traveled to deep space describes differently, but they all describe it. The moment when you look out the window and the Earth is no longer the vast, dominant presence filling your view. It has become something smaller, something distant, a sphere hanging in the dark, beautiful and fragile, and impossibly far away. For the crew of Artemis 2, that moment will arrive in a way it hasn't for any human being since 1972. And when it does, the reality of where they are will be unlike anything experienced in over half a century of human spaceflight. They are really far from Earth now. And everything about how the mission operates reflects that fact. The first and most immediate reality of deep space is the environment itself. Beyond the protective bubble of Earth's magnetosphere, the crew of Artemis 2 will be exposed to levels of radiation that are simply not experienced in low Earth orbit. The International Space Station, for all its distance from the ground, still benefits from a degree of shielding provided by Earth's magnetic field. In deep space, that shielding is gone. The crew will be exposed to galactic cosmic rays and the ever-present risk of solar particle events, bursts of radiation from the sun that can arrive with little warning. Monitoring how the crew's bodies respond to that radiation exposure in real time over a real deep space mission is one of the most medically significant things Artemis 2 will accomplish. The data gathered will directly inform how NASA protects future crews on longer missions, including the eventual journey to the lunar surface. Then there is microgravity. Weightlessness is not unique to deep space. Astronauts on the International Space Station experience it too. But the duration and context of Artemis 2 present their own specific challenges. How do the crew perform over the course of this mission? How does extended microgravity affect their physical condition, their coordination, their sleep, and their cognitive sharpness when they are operating far from Earth with no immediate support available? These are not abstract questions. On a moon landing mission, a crew member who is physically or cognitively compromised by the effects of their environment is a safety risk. Artemis 2 is the opportunity to gather real, human data on performance in deep space conditions, using monitoring and observation that no ground simulation can replicate. And all of this is happening inside Orion, a spacecraft that is, for the duration of this mission, the crew's entire world. Orion in this context is functioning as a deep space habitat, and that is a role it has never played with human beings on board before. The interior of Orion is significantly more compact than the International Space Station. For people, living and working together in a pressurized volume that offers very little in the way of personal space, for a mission lasting multiple days in one of the most hostile environments in the known universe. The life support systems that scrub carbon dioxide from the air, that maintain cabin pressure, that regulate temperature, that recycle water. All of them are being tested here under genuine operational conditions for the first time. Not in a vacuum chamber on the ground. Not in a simulation. In deep space, with 4 lives depending on them performing exactly as designed. There is something profoundly human about this phase of the mission when you consider it fully. For people, further from home than almost anyone in history, going about the work of keeping themselves alive and gathering the data that will one day let others follow. The checklists still get completed. The meals still get eaten. The observations still get logged. Life continues, in miniature, in a small pressurized capsule moving through the dark at thousands of miles per hour. And every hour they spend out there, every data point collected, every system that continues to function as it should, is another piece of the foundation on which humanity's future in deep space will be built. Everything that Artemis 2 has done up to this point, the launch, the systems checks, the translunar injection, the days spent in deep space, all of it has been building toward this. The moment the crew of Artemis 2 swings around the moon and sees it up close, with their own eyes, for the first time in over 50 years of human spaceflight. The closest approach brings Orion to within approximately 4,070 miles of the lunar surface. In the context of space, that is extraordinarily close. Close enough that the moon is no longer the distant, disk-like object familiar from Earth. It fills the windows. The surface becomes real in a way that photographs, no matter how detailed, can never fully convey. Craters that have existed for billions of years. Mountain ranges stretching across an airless landscape. Plains of ancient volcanic rock lying perfectly still in the total silence of space. The moon as it actually is ancient, vast, and waiting. No human being has been this close since the crew of Apollo 17 made their journey home in December 1972. And in the decades since, that proximity, that visceral, window-filling closeness to another world, has belonged only to memory and archive footage. The crew of Artemis, too, will bring it back into the present tense. They will look out of those windows and see something that fewer than 24 human beings have ever seen, and they will be seeing it fresh, in a new century, aboard a new spacecraft, as the harbingers of a new era of exploration. And they will be watching carefully. The crew will spend this phase of the mission observing and documenting the lunar surface with a scientific and operational purpose that goes beyond the profound personal experience of simply being there. What they see, what they photograph, what they record and report back, all of it feeds into the planning and preparation for Artemis 3, the mission that will actually put boots on the ground. Understanding the surface from this vantage point, seeing how the lighting falls across different regions, observing features of the landscape up close and in real time, this is reconnaissance in the most literal and meaningful sense. The crew of Artemis 2 are, among other things, scouts for the mission that follows them. But it is worth pausing on the human reality of this moment, because the scientific objectives, as important as they are, don't fully capture what it means. These 4 people, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, will be floating at their windows looking at a world that humans once walked on and then left behind. They will be close enough to see the very regions where the Apollo landing sites lie. They may be able to see, or know precisely where to look for, the places where human footprints still exist in the lunar dust, undisturbed for half a century in the total absence of wind. There is something quietly overwhelming about that. The past and the future of human exploration, visible simultaneously from the windows of Orion. And then the trajectory does its work. The moon's gravity curves Orion's path, the spacecraft swings around the far side, that place of total communication blackout, where the crew are more isolated from Earth than it is possible to be anywhere else in cislunar space, and then they come around the other side, and Earth reappears in the window. Home, distant and blue, exactly where the mathematics said it would be. Artemis 2 does not land on the moon. That was never the mission. But what the crew experience at closest approach is something that cannot be manufactured, cannot be simulated, and cannot be fully understood from the ground. They were there. They saw it. And now they carry it home. Sometimes, to truly understand the scale of something, you need the numbers. And when it comes to Artemis 2, the numbers are staggering. This is not a modest step beyond low Earth orbit. This is a journey of a scale that puts almost every other human spaceflight mission in history into sharp perspective. So let's talk about just how far and how long this mission really is. At its farthest point from Earth, Orion and its crew will be approximately 252,760 miles away from our planet. Take a moment to sit with that number because it is genuinely difficult to comprehend in human terms. If you could drive a car at motorway speeds without stopping, day and night, continuously, it would take you the better part of 6 months to cover that distance. The entire diameter of the Earth, the full width of our planet from one side to the other, is less than 8,000 miles. The distance Artemis 2 travels from Earth is more than 30 times that. It is a number that belongs to a different scale of reality than our everyday experience, and yet 4 human beings will be living inside it. To put it in its historical context, that distance makes Artemis 2 one of the farthest journeys human beings have ever made from Earth. The Apollo missions reached comparable distances during their lunar orbits, and the record for the farthest any humans have ever traveled from Earth was set by the crew of Apollo 13, not by design, but by the cruel mathematics of their emergency free return trajectory after the explosion that crippled their spacecraft. Artemis 2 approaches that territory, and it does so not in an emergency, but as a planned, deliberate act of exploration. The sheer distance from Earth that this crew will experience is, by any measure, extraordinary. Then there is the total distance traveled across the entire mission. When you account for the full trajectory, the climb out of Earth orbit, the arc across deep space, the swing around the moon, and the long journey back, Artemis 2 covers approximately 695,000 miles from start to finish. Nearly 700,000 miles. The circumference of the Earth at the equator is just under 25,000 miles, which means the crew of Artemis 2 will travel a distance equivalent to circling our entire planet roughly 28 times over. Laid out in a straight line, that distance would take you from Earth to the moon and back, with hundreds of thousands of miles left over. And all of that happens within a mission duration of 10 days. 10 days from launch to splashdown. In that single span of time, little more than a week and a half, 4 astronauts will travel further than almost any human being in history, swing around the moon, and return safely to Earth. When you break it down that way, the pace of the journey becomes almost as remarkable as the distance itself. This is not a slow, gradual drift through space. Orion moves fast, tens of thousands of miles per hour, and the mission is a continuous, dynamic exercise in precision navigation across an almost incomprehensible expanse. 10 days. 695,000 miles. A closest approach of over 252,000 miles from Earth. These are not just impressive statistics to list in a presentation. They are the actual, physical reality of what 4 human beings will experience aboard Artemis 2. They are the dimensions of the challenge, the measure of the commitment, and the scale of the achievement. And when Orion splashes down in the Pacific Ocean and the crew are pulled safely from the water, every single one of those miles will have been earned. Beyond the headline milestones of distance, duration, and the lunar flyby itself, Artemis 2 is quietly carrying out work that most people won't hear about, but which may prove just as important to the long-term future of human spaceflight as anything else on the mission. Tucked within the 10 days of flight are a series of experiments and technology demonstrations that are, in their own way, preparing the road ahead just as surely as the mission itself. Because Artemis 2 is not just proving that humans can go back to deep space. It is actively developing the tools and techniques that will make everything that follows safer, smarter, and more capable. One of the most forward-looking demonstrations on the mission involves laser communication. Traditionally, spacecraft communicate with Earth using radio waves, a technology that has served spaceflight well for decades, but which has real limitations in terms of the volume of data it can carry. As missions become more complex, as crews venture further from Earth, and as the ambition of what those missions need to transmit back home grows, the bandwidth constraints of radio communication become an increasingly significant bottleneck. Laser communication, by contrast, operates on a fundamentally different principle, using focused beams of light to transmit data at speeds dramatically higher than conventional radio systems can achieve. For future deep space missions, where high-definition video, complex scientific data, and rapid communication with mission control may all be mission-critical requirements, the ability to move large volumes of information quickly could make an enormous difference. Artemis 2 will test this technology in the deep space environment under real operational conditions for the first time. If it performs as hoped, it points toward a future where deep space communication is faster and richer than anything currently possible. Then there are the proximity operations, and this one is particularly interesting from a piloting perspective. During the mission, the crew will practice manually flying and maneuvering Orion in space, developing and validating the hands-on skills needed to operate the spacecraft in close proximity situations. This matters enormously for future missions where precise manual control could be the difference between mission success and failure. Docking with other spacecraft, approaching a lunar gateway station, or executing maneuvers that require human judgment rather than automated systems. All of these demand a level of practiced, verified piloting proficiency that has to be built up carefully. Artemis 2 gives the crew the opportunity to develop that proficiency in the real environment of deep space, where the feedback from the spacecraft is genuine and the conditions cannot be replicated on the ground. Every hour of manual flying practice completed on this mission is an investment in the capability of every mission that follows. And then there is perhaps the most sobering demonstration on the list, the in-flight test of Orion's abort system. The abort system is the crew's last line of defense in a launch emergency. If something goes catastrophically wrong during ascent, if the rocket fails, if there is an explosion, if the spacecraft needs to be separated from the launch vehicle in a fraction of a second, the abort system is what pulls the crew capsule clear and gives the astronauts a chance of survival. It is, by definition, a system you desperately hope never has to be used for real. But it has to be proven to work. Testing it in flight, under actual conditions, provides a level of verification that ground tests simply cannot fully replicate. It is a demonstration that is easy to overlook in the excitement of everything else Artemis 2 is doing, but its importance to crew safety is absolute. Laser communication pointing toward a richer future of deep space data. Manual piloting practice, building the human skills that automation alone cannot replace. Abort system verification, ensuring that the crew always has a way out. Each of these demonstrations is a piece of the larger puzzle, a mission that is not just making history in the present, but methodically, carefully, and deliberately building the foundation for everything that comes next. Artemis 2 is preparing for the future. Every single day of those 10 days in space. Every mission in the history of human spaceflight has been a stepping stone. Mercury proved humans could survive in space. Gemini proved we could maneuver, rendezvous, and conduct spacewalks. Apollo proved we could land on the moon. And each of those programs, as monumental as they were in their own right, derived their deepest meaning not just from what they accomplished in the moment, but from what they made possible afterward. Artemis 2 stands in that same lineage. And what it makes possible is nothing short of humanity's permanent expansion beyond Earth. The most immediate consequence of a successful Artemis 2 is Artemis 3. That is the mission where humans return to the lunar surface for the first time since 1972, where boots touch the moon again, where a crew descends to the surface and conducts the kind of sustained scientific exploration that the brief Apollo landings could only hint at. But Artemis 3 cannot happen without Artemis 2. Every system that Artemis 3 will depend upon, the Orion spacecraft, the life support, the navigation, the communication, the deep space trajectory planning, all of it has to be verified with a human crew first. Artemis 2 is that verification. It is the proof of concept that unlocks the moon landing. Without it, Artemis 3 is ambition without foundation. With it, the moon becomes genuinely reachable again. And the vision doesn't stop at a single landing. The broader Artemis program is designed around the idea of sustained lunar presence, not flags and footprints and a quick return home, but ongoing missions, extended surface stays, the construction of the Lunar Gateway Station in orbit around the moon, and ultimately a permanent human capability in cislunar space. The data gathered by Artemis 2, the systems proven, the techniques validated, all of it feeds into that longer arc. Every future crew that travels to the moon will benefit from what Artemis 2 learns. Every piece of hardware that operates on or around the lunar surface will owe something to the work done on this mission. But even the moon, as extraordinary a destination as it is not the final horizon. NASA and its international partners have been clear that the Artemis program is not an end in itself. It is a training ground. The technologies being developed, the operational experience being accumulated, the understanding of how humans survive and work in deep space over extended periods, all of it is directly applicable to the mission that lies beyond the moon. Mars. A journey that will take months rather than days, that will carry humans further from Earth than they have ever been, that will demand everything that Artemis is learning and more. The road to Mars runs through the moon, and the road to the moon runs through Artemis 2. It is worth stepping back, at the end of all of this, and letting the full weight of what Artemis 2 represents settle in. A crew of 4 human beings, traveling 250,000 miles from Earth, swinging around the moon, returning safely home. In the immediate sense, it is a test flight, methodical, data-driven, cautious in all the right ways. But in the larger sense, it is the moment humanity recommits to its future in space. not as a memory of what we once did, not as an aspiration for some distant, undefined tomorrow, but as a present tense, happening now declaration that we are going back, that we are going further, and that we are not stopping at the moon. This wasn't just a trip around the moon. It was the first step toward living beyond Earth.